Yes, need some muting done. Okay, so our next talk is going to be a keynote. It's going to be Tom Blenkinsop, all the way from Cardiff, who's going to give us a talk on more tectonic, structural, bigger scale viewpoint of not just the Bushveld, but the Great Dyke as well. So,
thanks very much, Dave. Yes, well, good afternoon. And as the previous speaker said, thanks very much for hanging around for this talk. Of course, giving a talk at this stage in the conference has got its disadvantages, but it's also got its advantages as far as I'm concerned. One of which is that after these 4 very intensive days of conference going, your critical faculties might be a little bit dulled, and I might be able to get away with a little bit more speculative material than otherwise. Anyway, the premise of this talk is indeed that we have the Great Dyke in the Zimbabwe Craton, geographically not so far away today from the Bushveld complex and Mapeo Farms complex. What can we learn from comparing these two world-class mafic intrusions? And I would have to say that this talk is triggered really by my collaboration with Andy Moore, and I'd also like to acknowledge all the other co-authors that are listed there. So I'm going to, this talk, by the way, I should say straight away, is mainly a review and very little sort of primary data or interpretation here. So that's, I suppose, okay for a keynote in a way. So I'm going to start off with making some comparisons, talking about geometry of those two intrusions. And then I'll dive a little bit deeper into intrusion mechanics for the Great Dyke and then the Bushveld and Mapeo Farms, and then end up with that very speculative material on supercratons and supercontinents, by which time, hopefully, you'll be fast asleep. Right. So in this view of the 2 cratons side by side, I've just rotated around the Capveld craton so that the Tabazimi Murchison lineament, the TML lineament, is roughly parallel to the Great Dyke, just to make some simple comparisons there. That lineament, whatever its role in the intrusion of the Bushveld and Mapeo Farms complexes is, which is a fascinating thing I've been learning a bit more about at the conference so far. Whatever its role, it's a transcrustal lineament on which those 2 intrusions sit, and it's parallel to and of similar length to the Great Dyke, which itself is parallel to a number of transcrustal transcratonic lineaments, which I'll talk about in more detail shortly. So there's that similarity to kick off with. For the Bushveld, of course, we have a now immensely detailed knowledge from the geophysics of its geometry, and that is sadly lacking actually for the Great Dyke. Obviously, from existing mining operations, we have a bit of a picture of the Lopolithic top of the Great Dyke, but at depth, we have to go back to the 1970s and Francis Podmore's fantastically detailed work for that time of gravity modeling, showing for the first time that the Lopolithic shape was lightly underlain in places in the 2 sub-chambers, for example, by a deeper feeder dike. And one thing we don't know very well at all is total volume of the Great Dyke. And so to estimate that, I've just taken one of his sort of more typical cross-sections and crudely sort of simplified it like that to give a cross-sectional area times the length of the dike to end up with this sort of figure here. Going about that another way, you can measure, of course, the map area of the Great Dyke, and you can take this 1 kilometer sort of depth of the Lopolithic part and arrive at actually quite a similar volume. So these dimensions are going to matter because they actually give us some insight into intrusion mechanics. And I want to just go through this rather complicated table here because this is the basis of a way of looking at how these intrusions have actually grown. So here we have the Great Dyke at the top and the Bushveld and the Mapeo Farms complex at the bottom in this table. We have some sort of linear estimate of their length. It's not very important. What is important is this column with the area, because the key to comparing intrusions of very different shapes, like the Bushveld and the Great Dyke, is to convert that area into an equivalent length. And we do that by taking the diameter of a circle, which has got the same area. And this is a really neat little trick to allow us to make meaningful comparisons between intrusions of very different geometry. So we can end up with this equivalent length parameter here, and then we can look at the maximum thickness and look at this critical ratio between the two. I'll just make a comment here that we've seen this figure before for the area of the Bushveld. Of course, that was from the Eales and Cawthorne paper. There's a couple of other estimates here which are definitely worth having a further conversation about. There's the geophysically constrained estimate from Janine Cole, and then there's the Smith and Maier estimate, and they produce different numbers. It's certainly true, and that ends up with generating quite a range of this critical L/T ratio. But they're not so different, actually. The only one that's very different is when we just look at the linear part of the dike and take that as a length compared to the 1 kilometer thickness that Francis imagined for the deep part of the dike width. So we have those values there, and the importance of that is that we can now go to the scaling relations paper by Sandy Crudden and co-workers, in which they are assembling a huge database of all kinds of different intrusions, and they're plotting the thickness in meters on this vertical scale, logarithmic scale, against the length, again, in meters on the horizontal axis here, for loads and loads of different intrusions, and identifying some really fascinating trends on this plot and interpreting them in terms of intrusion mechanics. So let's put on the Bushveld and the Mapeo Farms complex, depending on the different area estimates there, of course, fitting right into the top right-hand corner as we would expect in this plot. And in fact, I suspect that some of those gray symbols from the Crudden paper are actually from the Bushveld. Unfortunately, with that paper, that data set is not published, unlike the Smith and Maier compilation, so we don't actually know. And we can then also put on the Great Dyke, depending on whether we treat it as a sill, there it plots there, and as a dike here. So how do those points fit in with the interpretation that Crudden and others are offering? Well, the first thing that is interesting is that for the very largest intrusions in the Crudden compilation, they suggest that the maximum thickness possible, or at least the maximum thickness known for such a layered intrusion, would be about 10 kilometers. And they make the rather subtle and enigmatic comment that that is between a half and a third of the thickness of the crust. So suggesting really that there is some upper limit to the thickness of major intrusions governed by their relationship to the rest of the crust. And of course, the Bushveld and in fact, the Mapeo Farms complex on its own fit roughly on that trend. For slightly lower sized intrusions, a different trend is evident on the compilation from Crudden and others, and that is an increasing length and thickness together, and that is interpreted to reflect a sort of stage of growth which involves expanding the length or the area of the intrusion more than its thickness, because the gradient of that line is a little bit less than the one-to-one that would be true for an equivalent expansion of thickness and length. So that's what they interpret the data to mean, and it's interesting to see that the Great Dyke fits roughly on that transition between those two regimes when treated as a sill. When treated as a dike, it's right out there. Actually, many of these points on the bottom trend here are actually dikes as well, so it's not surprising that it fits in that sort of part of the plot. What I really want to use this diagram to say is that apart from perhaps telling us something about the way these intrusions may have grown, it is also true that they fit in with the rest of the data. So a comment that Julian Pierce made yesterday about the about the Bushveld not necessarily being particularly special in some characteristics, he was referring to his lip fingerprinting, is also true to some extent for the geometry. The geometry fits in with trends that we can see in other intrusions. Okay, so that's the general comparison. Let me carry on now to be a bit more specific about intrusion mechanics for the Great Dyke first. And I'll just point out to begin with that the Great Dyke is, of course, flanked by the Vermeulen Dyke to the west and the East Dyke to the east, for much of its length, and also that these features are parallel to a huge set of transcratonic fractures, the Popotecki fracture set, and probably formed contemporaneously with the Popotecki fracture set is another set of fractures, dextral, with apparent separations, the Mushandiki fracture set. And Jim Wilson, in his wonderfully titled paper, A Craton and Its Cracks, some of the history of the Zimbabwe craton, is that those two faults, in fact, did form indeed as a conjugate set with this sort of northwesterly directed maximum principal stress. And then for the intrusion of the Great Dyke, there may have been a slight rotation in the direction of maximum principal stress. So what caused that principal stress setup? Well, of course, to the south of the craton is the northern marginal zone of the Limpopo belt. We know very well that during the latest Archean, there was thrusting of the northern marginal zone over onto the craton. There was generally a northwesterly directed sense of movement on that huge thrust, the North Limpopo thrust zone, which exhumed the granulite facies of the Limpopo belt. And less well known is that to the north of the craton, actually, in the late Archean, poorly dated, is another orogenic belt, the Funzi belt. This was identified by Mike Vignew, worked on by him, which is the product of the Ngawi orogeny. So, in fact, the craton in the latest Archean was in a pincher, in a pincher movement between those two orogenies to the north and the south. So, what we're really working around to saying is that in some way these stress systems have acted as a trigger, potentially have acted as a trigger for the intrusion of the Great Dyke. A little bit more detail and some primary field data here on the Limpopo belt story. Throughout the whole of the northern part of the northern marginal zone, there's a remarkably consistent set of meter scale shear zones, beautiful simple shear zones, which have got strike slip movements on, and they fall beautifully into two sets, and sort of northerly directed set with sinistral movement and a northwesterly directed set with dextral movement, just like the Popotecki fracture set and the Mushandiki fracture set. And if we plot them up, you can see that they fall nicely into dextral and sinistral plate orientations on the stereonet, and we can do a kinematic interpretation to find the shortening direction for all of those, and it turns out to be this north-northwest directed shortening, very much in line with what Jim Wilson said. Now, what I really want to say about all of that is that it doesn't actually matter very much what the specifics of the shortening direction are. And this is because when we come to reactivate a fault or a shear which is pre-existing, either we have reduced its tensile strength, or we have reduced its coefficient of internal friction. And these Moore diagrams tell us that the consequence of that is that we can reactivate features with a wide range of orientations for a given stress system. And that's really the bottom line. And this diagram here is another way of illustrating exactly the same point. So what this diagram is a radial or polar plot of the slip tendency, the propensity for a fault to slip for a given stress orientation, or the dilation tendency, the propensity for it to open up as a function of direction. And I've just assumed a northwest direction of maximum principal stress here. And if you look at the orientation of the Great Dyke in this line here, you can see that actually for that stress system, the Great Dyke has got an almost full slip tendency, but even the dilation tendency is well over a half. So it doesn't really matter what the precise orientations are. If we have an oblique feature, pre-existing feature with a reduced strength, we are easily able to reactivate it for that sort of stress system. All right, so on to the Bushveld Malopo Farms complex now. I want to talk about the TML lineament. I've learned a lot about it so far in the conference, but I do want to refer to you to the work of Clark and others, in which they argued from a variety of lines of evidence that the TML was a feeder structure. We may have heard a different perspective on that from Ian yesterday, but it's also important to point out, of course, it's not just the TML that we may be talking about. We may be talking about the Hout River shear zone, as Ian mentioned yesterday. We may be talking about the feature which Judith just talked about. I can't remember the name of that, Judith, your shear. Sugar bush. I think the one further south than that. Yeah. Is it sugar bush? Right, yeah, okay, that one. And also, in fact, to the north of Palala and Chappies shear zones. All of those are major crustal structures in a fairly similar orientation. What Clark and others did was a very neat structural way of deducing magma transport directions from the finger-like structure and the overlapping of those fingers. And I think this is a really important piece of work, because it is about the only direct way that we have had, we know of, or that has been used to find magma transport directions. And their magma transport directions, which I've enhanced in red arrows here, are broadly speaking away from the TML lineament. So I think that's a very interesting and promising structural approach that could have a much wider application. As far as the Mapeo Farms complex goes, the geophysical work there really identifies that there's a number of major shears which go through the Mapeo Farms complex. And if we look at the interpretation of the gravity here, we've got a potential feeder structure along those shears, and they are in fact splays really of the TML lineament. So they seem to be important. So once again, we've got a story potentially of one or maybe more than one major crustal structures pre-existing, which may have acted as feeders. And we therefore want to think about the tectonic situation, the bigger picture tectonic situation, which may have reactivated those features. Well, actually, as it turns out, in the early Proterozoic, we have got a whole lot of tectonics going on around the Zimbabwe and Capval Craton. Starting up in the northwest, which I know perhaps a bit more about, we have the Magondi orogeny, in which the rocks of the Magondi were thrust over onto the Zimbabwe Craton at around about this time. There was also intrusive activity. As we go to the west of the Capval Craton, of course, we end up in the Kais Belt, which again has got metamorphic ages of this age. And even more critically, we know that those lineaments in the Limpopo Belt, the Chappies-Palala shear zone, the Hout River shear zone, were reactivated in that early Proterozoic orogeny as dextral shear zones. So there's no problem at all in saying that we have, again, this potentially tectonic triggering of those lineaments, which might be related to the intrusion mechanics of the Bushveld and Mapeo farms. Just to emphasize that, here's a compilation of mineral ages from Jan Kramers and Huri, and all the black symbols that you can see in this map of the central zone, the northern marginal zone, the southern marginal zone, the Limpopo Belt, all of those are early Proterozoic mineral ages, testifying to the intense tectonic activity that was going on. And of course, in the middle of the central zone, there was also very high-grade metamorphism in that early Proterozoic event. So even bigger picture coming from Sharad Masters, what did all this mean sort of on a more sort of continental scale? Well, Sharad's beautiful phrase here is that the Magondi, the Kais orogeny, reactivation of the shears in the Limpopo Belt is due to the arrival of terra incognita from the west against the Zimbabwe and the Capval Craton, and associated convergent tectonics, and potentially, and then reactivation of those shears in the Limpopo Belt. And that is also, broadly speaking, the story from the paper by Paul Silver and others, which has already also been shown in the conference previously. And in this paper, they're making the case that a number of times there may have been oblique convergence, first of all in the late Archean with the Great Dyke, and then subsequently in the early Proterozoic with the TML and the Bushveld intrusion. So the critical ingredients for this triggering is the pre-existence of structures at an oblique angle to the direction of convergence. A slightly different take on that from the Clark and Al paper was that maybe the Bushveld was in an extensional or back arc zone. And finally, just from the Silver et al. Paper, the point that if you look at the mantle anisotropy, it's interestingly enough parallel to the Great Dyke and the TML. And that suggests actually that these structures might have an even more fundamental sort of mantle control on them, and they pre-existed the intrusion of those two bodies. So finally, just the really speculative stuff now, so you can certainly go to sleep for a bit. What happened after the intrusion of the Great Dyke was that apparently, not very long after, a number of Archean cratons assembled together. This is one version of that construction, and that's largely based on the sort of correlation of Dyke swarms in these different cratons. And here's another version of that, so that a number of these Archean cratons might have accumulated together, perhaps in fact in two different places in the late Archean on the Earth. And these are called supercratons rather than supercontinents, because they don't have the same scale in terms of area that we know from the conventional supercontinent cycle. So that happened probably by about 2,500 million years ago, so about 75 million years after the intrusion of the Great Dyke. And shortly after the intrusion of the Bushveld complex, the Mapeo Farms complex, the assembly of the world's first supercontinent started to happen from about the time of intrusion onwards till the around about 1,600 million years ago, the world's first accepted supercontinent formed, which is called in this diagram the Nuna supercontinent. It's more commonly known as the Columbia supercontinent. So that followed, or at least the start of that process, also followed to some extent after the intrusion of the Bushveld. Now, I'm not going to say what the exact cause and effect of those relationships are. I'm just going to point them out, because that will lead nicely onto my conclusion slide here. So just to go over where we started, intrusion of pre-existing crustal structures seems to be very important for both the Bushveld and the Great Dyke. Convergence at high angles, or oblique angles rather, to those structures always has got the potential, if those structures are weaker, for high slip and dilation tendencies, which is what we mean by this concept of tectonic triggering. We've looked at the dimensions of the structures. We see that they're compatible with other very large intrusions, and therefore that the Bushveld and the Great Dyke are not, in that sense, particularly exceptional. We've seen that supercratons occur. At least one supercraton may have formed involving the Zimbabwe craton shortly after its intrusion, and the Nuna or Columbia supercontinent formed a rather longer time after the intrusion of Bushveld. So the bottom line here that I really want to say is the transition from supercratons to supercontinents is quite commonly thought of nowadays as marking a fundamental shift in global geodynamics from some sort of lid tectonics. Sluggish lid is a popular one these days, as opposed to mobile lid, to full on plate tectonics. So this transition at the end of the Archean is quite commonly viewed in that light. And it's interesting, therefore, that in terms of intruding major layered mafic, ultramafic intrusions, it doesn't seem to matter whether we are in the sluggish lid mode, assembling supercratons, or whether we're in plate tectonics mode, assembling supercontinents. In other words, the processes that are generating these huge intrusions are not really dependent on any particular mode of global mantle geodynamics. And I'll leave it at that, hopefully.
Okay, thank you, Tom. Sue, then Moose. Or Moose first.
Hi, Tom. A very simple observation. If you look at the Bushveld, the lower part from the basically the upper zone downward appears to have been intruded in a somewhat compressional environment, which you can see folds within the floor and so on and so forth. And then when you get into the upper zone, there is a whole Dyke swarm, so it looks like the whole thing relaxed and you went into a slightly extensional environment at that point. It's
Thanks
just
very
a
much. I heard you mention that yesterday, and I was intrigued, and I find that very interesting. And of course, you've got to do that within a million years or so. So that just illustrates indeed that I've been painting a very broad brush here, because I've been throwing around ages with tens of millions of years. But things can change for sure.
So,
thanks, Tom. I really I appreciate that in terms of the LLSVP model that we've been developing. Of course, we can't push it that far back in time, but the fact that you're saying the tectonics on the surface is not affecting what's, how it's being generated at depth is kind of in line with what we're saying. So
Great.
Like that very much. Thank you.
Well, you went to sleep anyway.
yeah, Bruce.
Thanks, Tom. Your first bullet point there, you suggest that the Great Dyke is intruded along pre-existing crustal structures. Those are the northeast, southwest sort of general trends, same as the Dyke. When do you see those forming?
Okay, well, I think because they are so compatible with what was going on in the Limpopo belt in the latest Archean, I think they probably formed very shortly before.
Okay. When you talk of the Limpopo belt, the diagram you had seemed to suggest that was all exclusively in the northern marginal zone. Is that correct? One of the earlier diagrams you had seemed to suggest that all of that particular set of faulting was in the northern marginal zone. Is that correct?
Yes, it would only be in the northern marginal zone because further south in the triangle shear zone and further south, it's all overprinted by the early Proterozoic.
Okay. All right. Thank you, Tom. Right. Do you still want me to do one, Wolf? Still want me to do one? Okay. All right. So it's a full keynote talk, so it's 45.